Okay, so we've established in the previous lecture the first step of these three-phase voltage outputs. So now let's see what the next step will look like. So remember that in the previous step we said that we were going to switch Q1, Q4, and Q5 on. So now let's see what happens if instead of switching Q5 on the third leg, if we switch Q6 on. So let's say then that state 2 is going to be Q1 on, Q4 on, and Q6 on. So again, the only difference from this state and the previous state is that in the previous state we switched Q5 on, and now we're going to switch Q6 on. So let's see what that does for the output voltages. So again, we got to draw the equivalent circuit based on the transistors that we're switching on. So we're going to have Vn, and then we said that Q1 is on, but now Q4 and Q6 are on. So then the equivalent circuit will look like this, where this would be VA, and these two at the bottom would be VB and VC, with the negative terminals on the neutral one. So this will be minus, plus, minus, plus. So essentially we've connected the positive terminal of both VB and VC to the negative terminal of Vn through transistors Q4 and Q6. And again, we're leaving Q1 on. So we're leaving the positive terminal of VA connected to the positive terminal of Vn. So now let's go ahead and do the same thing that we did for the previous state. We're going to calculate the voltage at the neutral. So we're going to calculate Vn. And so just like in the previous state, we're going to do just a simple voltage divider. Vn is going to be equal to Vn. But now we're going to have RB. Let me just do R, because we've established that RA and RB and RC are equal to each other. So I'm just going to write down R from now on. So Vn R in parallel with another R. So these two would be RB and RC over the sum of all of them, which would be R, this being RA, plus the parallel of RB and RC. So this will be equal to Vn times, and then again, remember that if two resistors are equal to each other and they're connected in parallel, then the equivalent resistance of the parallel combination is going to be equal to half of those resistors. So this is going to be 0.5 times R over R plus 0.5, so 1.5 R. So R's cancel out, and we add that Vn for this second step when Q1, Q4, and Q6 are on is going to be equal to Vn times 0.5 over 1.5, and all of this is equal to basically Vn over 3, or 1/3 of Vn. So now let's see what the output voltages would look like. So VA is connected, again, the positive terminal of VA is connected to the positive terminal of Vn. So VA is going to be equal to Vn minus whatever is connected to the negative terminal of VA, which is the neutral, which is at 1/3 of Vn. So minus Vn over 3. So VA then for this second step would be, let me just write this down, 2/3 of Vn. Right, so Vn minus Vn over 3 is 2/3 of Vn. So VA is going to look like this. It's going to be 2/3 of Vn. And now let's calculate VB. So VB is going to be equal to, so again, the positive terminal of VB is still connected to the negative terminal of Vn, which we're taking as the reference. So it's going to be equal to 0 minus the neutral, which is Vn over 3. So VB is going to be equal to minus Vn over 3. And let's also calculate VC. So VC is going to be equal to, so it's going to be just like VB, 0 minus the neutral, which is Vn over 3. So this is going to be equal to minus Vn over 3. So then VC would look like this, goes down to minus Vn over 3. And then let's also draw VB. So VB went from minus 2/3 Vn to minus 1/3 Vn. So VB is going to look like this. So now let's do one more step in the waveform, and then we're going to start seeing a pattern, and then we're going to be able to figure out what the remaining of the waveforms are going to look like based on that. So we're not going to calculate any more steps. We're going to see from the 3 first steps what the last third steps are going to look like, just based on the pattern. So let me go ahead and erase some things here. Okay, so now let's say that for state 3, we're going to have Q1 on, Q3 on, and Q6 on. So now you may start noticing a pattern here. In the previous state, we had Q1, Q4, and Q6 on. And now we have Q1, Q3, and Q6 on. So in every state, we're only changing one of the legs. Remember that in the first state, we had Q1, Q4, and Q5 on. And in the second state, we had Q1, Q4, and Q6 on. So we switched the third leg from 5 to 6. And now we're changing 4 to 3. So basically, during every state, we're changing only one leg. So now let's see what the equivalent circuit will look like. So we're going to have, again, Vn plus minus, and then Q1 is still on. So VA is connected to the positive terminal of Vn. So now Q3 is on. So the positive terminal of VB is now connected to the positive terminal of Vn. So this is going to be VA over here and VB over here. And then we also have Q6 on. So we know that the positive terminal of VC is connected to the negative terminal of Vn. So now this is going to be VC over here. And then again, minus plus VC. So now let's see what the neutral voltage would be. So we're going to have Vn times RC. So I'm just going to write down R over the parallel combination between RA and RB. So again, I'm just going to write down R in parallel with R plus RC. So R, so this is going to be equal to Vn times R over 1.5 times R. Because again, R in parallel with R is 0.5, and then plus R, that's going to be 1.5 R. And by the way, I don't think I mentioned this, but this symbol right here is a symbol for a parallel combination. So when I write that down, that means that we have those two resistors in parallel with each other. So this is going to be equal to 2 Vn over 3. So basically 2/3 of Vn. Now let me go ahead and erase these equations on the right so we can calculate VA, VB, and VC again. So now we would have that VA is still connected to Vn, so this is going to be equal to Vn minus the neutral voltage, so 2/3 of Vn. So 2 Vn over 3. So this is equal to 1/3 of Vn. So now VA comes back to 1/3. And VB is going to be equal to Vn, because now the positive terminal of VB is connected to the positive terminal of Vn, minus the neutral voltage, so 2 Vn over 3. So this is going to be equal to 1/3 of Vn. So now VB jumps to 1/3 of Vn. So from minus 1/3 of Vn to plus 1/3 of Vn. And lastly, VC is going to be equal to, now the positive terminal of VC is connected to the negative terminal of Vn. And again, we've taken that as a reference. So this is going to be 0 minus the neutral, which is 2/3 of Vn. So this is equal to minus 2/3 of Vn. So this goes down to minus 2/3 of Vn. So now you can start seeing a pattern. This is why I said that we're just going to calculate the first 3 steps, and then we can see from the pattern what the rest of the waveforms are going to look like. Because we see that the voltages go from, let's say, for example, VA, it went from 1/3 of Vn to 2/3 of Vn, then back to 1/3 of Vn. And then we saw that VB goes from minus 2/3 of Vn to minus 1/3, and then it jumps from minus 1/3 to plus 1/3. And if you see on VC, that actually happened as well, going negative. So it went from 1/3 of Vn to minus 1/3 of Vn. So we know that we're not going to have a step that's at 0 volts. So we saw that the voltages went from 1/3 of Vn to plus 2/3 of Vn, back to 1/3 of Vn, and then they jump from 1/3 to the opposite 1/3. So if we have a voltage at positive 1/3, then it jumps to minus 1/3. And likewise, if we had a voltage at minus 1/3 of Vn, then it jumps to 1/3 of Vn. So just from the symmetry of this, we can see that VA for the next step is going to go from plus 1/3 of Vn to minus 1/3 of Vn. So VA is going to look like this. And then it's going to go from minus 1/3 to negative 2/3. Then back to negative 1/3. And then it's going to repeat after that. Likewise for VB, then we have it now at 1/3 of Vn. So then it's going to go to 2/3 Vn. Back to 1/3. And then it's going to jump from 1/3 to minus 1/3. And then of course repeats after that. And then VC, we have it at minus 2/3 now, so it's going to go back to 1/3, or excuse me, minus 1/3. Then it's going to jump from minus 1/3 to plus 1/3. And then it's going to go to 2/3. And it's going to repeat after that. And this, of course, I didn't draw it, but this would be coming like this. VA would be before 0, it would be minus 1/3. And then after 2 pi would be plus 1/3. So again, these waveforms repeat. And then VB will look like this. It's a minus 2/3, so we'll go back to minus 1/3 and it's going to repeat there. And after 2 pi, it's going to go to minus 2/3. And likewise for VC. So it's going to go over here, and then over here, and repeat. So a couple of things that we can note here. One is that we don't have a step that's a 0 volts, like we had in the single phase inverter example. However, remember that the single phase example had only 3 steps. So it had 0, plus Vn, 0 again, minus Vn, back to 0. So even though here that for the 3-phase inverter, the voltages don't go to the full Vn and the full minus Vn, they're actually less distorted, because now we have, instead of having just 3 steps, we actually have 4 steps. So now we have plus 1/3 of Vn, plus 2/3 of Vn, minus 1/3 of Vn, and minus 2/3 of Vn. So even though the voltage doesn't go up to the full Vn and the minus Vn like in the single phase inverter, these waveforms are actually less distorted because we have more steps. So they resemble a sine wave more closely than the single phase example that we looked at. However, it is a disadvantage that we can't use the full DC input voltage. But we can see here that by using only 6 transistors from a DC source, we can actually make a 3-phase voltage output, which is very useful, and all things considered is not that complicated to do. And also, if we're trying to achieve a certain peak voltage for the 3-phase voltages, we could just make the DC voltage higher or lower. So if we had a means of controlling the DC voltage by using a DC to DC converter, we can couple that with this 3-phase inverter to achieve a peak voltage magnitude that we want.